Welcome to the first unit the first lecture in Unit 1 called How Much Does It Mass? It says, I can calculate the motion of heavenly bodies, but not the madness of people. It's a famous quote by Isaac Newton. So the learning goals for this particular presentation are that students will be able to describe and give examples of Newton's laws of motion, distinguish between mass and weight, and use the equation F net equals ma. So, what we already know. You should know from middle school that force is a push or a pull on an object, that forces can change the motion of an object, and that there are many different forces, including gravity, friction, electric, and many others. So that's information that was covered in 8th grade, 6th grade, and so on. So here you see an example of Luke Skywalker using the force to pick objects up and move them. So, what we learned in the lab. We learned that mass is measured in kilograms. Now, many of you may be familiar with mass being measured in grams from chemistry, but that's not the case. Grams is not the standard unit, it's actually the kilogram. You should also be familiar that weight should be measured in newtons, and that whenever you whenever you create a graph of force versus mass, whenever you have a suspended object, it gives you a constant slope of 9.8 on Earth. Now, that number can be different if you're not on Earth, but I'm going to assume that everybody listening to this is on Earth. So, balloon rockets. We actually did an engage activity in which we said that the balloon remained motionless before air began to escape. So when you first set up the balloon rocket, before you let it go and let it pinch, it didn't move forward at all. There were no forces on the ball, resulting in no motion. Okay. Whenever you released the balloon and then air began to come out, there was all of a sudden a force being exerted on the balloon, and that the object began to accelerate or move forward. It turns out that the more air escapes, the greater the acceleration. So if you were to kind of widen this out and allow a greater amount of air out at the beginning, it would accelerate with a greater rate. So now, we have Aristotle's laws of motion. Now, the first thing you should notice is there's a big X through this. That just indicates that it is no longer believed. So I need to give you a historical perspective and tell you what Aristotle believed, but this is no longer considered to be valid. What Aristotle believed is that objects have natural motion because they have a natural place. In other words, if you take a rock and put it in the air, that rock's natural place is on the ground, so it will seek to move to its natural place. Now, that was natural motion. Now, you can take something away from its natural place by exhibiting what we call violent motion. So, example, if I have a box on the ground and I pick that box up into the ground, I exhibited violent motion on the box to make it move up. Now, Aristotle also believed that the speed of an object is directly proportional to the force exerted on it. So, in other words, if I have a box and I push it really hard, it gets faster. And that's true to some extent. But you know that's not always the case. If you roll a ball along the hallway, the ball will keep moving even when there's nothing pushing on it. So that's why Aristotle's laws of motion is no longer believed. It's no longer considered to be valid. But you do need to know the historical perspective. Now, balloon rockets part 3. After the balloon lost all of its air, it continued to move. This is another refutation of Aristotle's laws. Aristotle said an object that doesn't have any force on it will come to a stop. But whenever the balloon ran out of air, it continued moving in the direction that it was initially moving at the same speed. Now, it eventually slowed down, and we'll talk about that a little bit later, but for now, we're going to say it continued to move at the same speed. Newton. Okay, Newton is the most famous person that you're going to talk about in physics. Okay, he contributed significantly to optics. He was the first person to kind of do scientific investigations with splitting of light with using a prism into all the colors of the rainbow. Okay, he developed the laws of motion that we're talking about in this particular unit, in which we relate force and motion together. He came up with what is called Newton's law of universal gravitation to explain gravity, and that's what he's most famous for. He, along with a German mathematician named Leibniz, at the same time invented what we now know as calculus. And then he also made significant contributions to what we call fluid mechanics. So he's famous for having said, if I've seen further, it's by standing on the shoulders of giants. What Newton said is he recognized the contributions of those that came before him, like Galileo. And he extended their information and made his own contributions to physics. Now, law of inertia part 1. Objects are lazy. That's the easiest way to remember it. Objects are lazy. An object at rest will stay at rest unless acted on by a net external force. So for example, I have a ball right here. This ball will never, ever, ever move unless an object comes and pushes it. As soon as an object exerts a force on this object, it begins to roll in a particular direction, whatever the roll of the push is. But until then, it's going to stay there forever. Now, the law of inertia part 2, once again, we're talking about being lazy, is that objects don't change. If an object is moving, let's say that this 8 ball is rolling along the floor, it will continue to roll along the floor forever unless exerted on by a net external force, like if it runs into a wall. If it runs into a wall, this wall will exert a force on the ball, causing it to stop its motion forward. Okay, so an object in motion will stay in motion unless acted on by a net external force. And now some of you are thinking, well, I roll a golf ball along the grass and it comes to a stop, so how does this work? Well, remember, we're talking about a net external force. Okay, we're going to talk about this a little bit later, but when you have grass, there is a force that is exerted between the grass and the ball that you may know as friction. Okay, don't account for friction when we're talking about the law of inertia. Force. Force is any push or pull that results in a change in the object's motion, direction, or shape. You can push on a can, like an empty soda can, and the object doesn't move, but instead it changes its shape. So force is measured in newtons, and it's measured with a spring scale. Okay, there's also some force meters that you can use, or a force plate, but the standard one is a Newton spring scale that you see there. Mass is a measurement of the inertia or the resistance to the change in motion. Mass is measured in kilograms as a standard unit and is measured with the balance. Developing A1. It says, which object has a greater inertia, a car moving down the highway or a cruise ship at rest? Now remember, when we're talking about inertia, we're talking about mass. So it doesn't matter if the car is moving or if the cruise ship is at rest. We're trying to talk about which one is going to resist a change in motion to the most. Cruise ships are much, much, much larger. They have much, much more mass than a car. You generally think of a car as being fairly massive, but you can fit hundreds of cars inside of a cruise ship. So because of that, we would say that the car has less inertia than a cruise ship, or the cruise ship has more inertia than the car. So now we want to compare mass and force. Now a lot of times these two things tend to be mingled in a way which they shouldn't. Force, an example of a force is weight. Okay? And a lot of people say, oh, I weigh this much. You shouldn't be doing that. You should be saying, I have this much mass, because your weight can change based on where you are. So a force can change based on acceleration. Okay? Force can change based on an acceleration, where mass is a constant. Now they are related to one another. Generally speaking, as mass goes up, force goes up. So they're tied together. There's a direct relationship between the two, but they're definitely different and they shouldn't be used interchangeably. Proficient A3, it says NASA is investigating a round-trip mission to Mars. During the initial mission assessment, the weight of the cargo is provided. Explain why this information, although useful, is not as relevant as mass. Now remember, NASA deals specifically with sending objects out into space. The only way that the weight becomes important is weight is mass times gravity. Because of the nature of this particular mission, the gravity will change as you go from Earth, where gravity is one thing, to Mars, in which gravity is something else. In between, there's even less gravity in space. So because we have the weight that's provided to us on Earth, we could use the weight to find the mass on Earth, which is the same as the mass on Mars. But we need to make sure that we understand the importance that weight on Earth is different than weight on Mars. Mass is the one that's constant regardless of the gravitational field. Mastery. It says a rock attached to a string is swung in a circle as shown. What is the direction the rock will fly if the rope is suddenly cut? Now, some of you may have done something like this before. If you've ever swung something over your head and then let go, you should realize that whenever you cut this wire, the rock will go. Now there's no more forces acting on the rock. So the rock will go in whatever direction it is going at that particular moment. And people say, oh, that means it's going to continue going in a circle. No. When an object moves in a circle, its velocity, or how fast it's going, is always tangent to the circular path, which means that the velocity in this case is right here. So if you were to suddenly cut the string that holds the rock in a circular path, now the rock is going to continue moving in that direction in a straight line. This question is Mastery A5. It says describe the motion of the box on the ramp. So whenever we're trying to describe the motion of a particular object, we have to look at what's called the net forces, or what are the total of the forces acting on the object. Now if you were to look at this, you see there's a force going up, a force going backwards, and a force that's going right here. As a result of this, you can actually combine the forces to describe the motion of the object. If you were to look at it, we have to compare the sizes of the forces. This force right here and this force right here. You notice that the force that's going down is actually smaller. You say, how do I know that? Because I can measure the length right here. It's smaller than the object or the force that's going up. So because of that, I can say that the force going up is larger and that the object will move up. But that's only part of the question. So now we also have a force that's moving to the right, and we have a force that's moving to the left. If you were to compare those, you would see that the rightward force is bigger than the left force. So because of that, I would say that the right force is larger, and so I would say that I would be moving up and to the right, or if you were to look at it this way, you're moving up the ramp like that. Now we have Newton's second law, and Newton's second law says that force is directly proportional to acceleration. Okay, so twice the force results in twice the acceleration. This makes sense. If you push a lawnmower with a force of 10, it goes so much. But if you push it with 20, it's going to go twice as much. So now twice the force is twice the acceleration. Now there's a second part of Newton's second law as well. It says that mass is inversely proportional to acceleration. So in other words, if I have one mass, I can push it with a force and it'll accelerate this much. But if I were to double or triple that mass, okay, now the object is much, much larger, and so if I were to push it with the same force, it's not going to go nearly as much. Think about it this way. If you were to push a pencil across your desk with a certain force, it would accelerate. If you were to exert that same force on a car, it wouldn't accelerate nearly as much. So we can combine those two, and we can get Newton's second law of motion. Newton was able to take these observations and get the equation F net equals ma. Now we're going to talk about this net part a little bit later. So for now, let's just kind of cross it out. It's still there, and we're going to address that in the second video. But for now, we're just going to say force equals mass times acceleration. Okay, so we have F is a force, which is measured in newtons, and we've already talked about that. The only thing that we didn't address directly is mass, or excuse me, acceleration, which acceleration comes from the previous unit. Remember, acceleration is the rate of change in velocity. It's measured with an accelerometer. So let's look at some examples. The first one says a car is being towed with a chain capable of exerting a force of 4,000 newtons without braking. What is the maximum acceleration the car is capable without breaking the chain? So if you look, we always underline our numbers, and we're trying to circle what we're looking for. So I'm going to write it out, and I'm going to say I'm looking for acceleration. I know the mass is 1,000, and I know that the force is 4,000, because that's the most force that I can put on it without it breaking. I would use the equation F equals ma, and I would plug in 4,000 equals 1,000 a. At this point, you would have to divide both sides by 1,000. When you divide both sides by 1,000, you get 4 meters per second squared is equal to the acceleration. Now we have a proficient level question. Remember, proficient level questions are going to be just a little bit harder. It says, determine the mass of an object when a 20 Newton force is applied. So when you have a 20 Newton force, you're looking specifically at this point. It actually isn't going to matter, but whenever you look at 20 Newtons, you've got that right there, and it results in an acceleration of this. So I've got A and 20. Now some people will be tempted to go ahead and find the slope of this particular graph. Now if you find the slope of this particular graph, it would be A divided by F, because I've got acceleration and I've got force. Remember, the equation is F equals ma. Okay, it's going to be very difficult to get to, if we divide both sides by F, okay, you get A divided by F, m equals 1. It doesn't really mean anything. Even if you move the m to the other side, you're going to have 1 over m, and that doesn't really mean anything. So we're going to cross that out. Okay? So we know that we're not going to find the slope. But what I can do is I can say f is equal to 20. I can say that a is equal to 5, and I can solve for the mass. Equation is F equals ma. Plug your numbers in, you'd say 20 is equal to m times 5. Plug it in, divide both sides by 5, you get mass is equal to 4 kilograms. Excuse me, 4 kilograms. Now we have a mastery level question. Remember, mastery level questions are the ones that you need to get 100. So now it says a 10 kilogram box is accelerated using a force of F. Notice how I don't know what F is. A 40 kilogram box is accelerated using the same force F. What is the ratio of the acceleration of the boxes? Okay, so remember, both of them have the same F. So that's the same value. So instead of saying F equals ma and F equals ma, I'm going to say that the mass and acceleration of the small box is equal to the mass times the acceleration of the large box. Now I can plug in. I can say 10a1 is equal to 40a2. And I can solve for the ratio. The ratio that you have here would be divide both sides by 10. Okay, when you do that, you're left with a1 is equal to 4a2. What that means is that the acceleration of a1 is 4 times greater than a2. Because let's say, for example, that the acceleration of a2 is 2, that means the acceleration of a1 is 8. Because at this one, you have to multiply by 4 to get the same acceleration as a1. Now let's take a look at balloon rockets again. It says the air was the force causing the balloon to move. So if you were to look at this, the balloon was clearly propelled forward, but the air was actually escaping out the back. So how can the air escaping out the back cause the balloon to move forward? The reason why is for every force, there is an equal and opposite reaction force. Okay, this is the last of Newton's 3 laws. It says for every force, there's an equal and opposite reaction force. For example, if I were to go ahead and push a wall, the wall would push me back with an equal and opposite force, so I would go backwards. Now, if you've ever seen, this is a famous scene in Return of the Sith, where you see Anakin and Obi-Wan Kenobi fighting, and there's a scene, or there's a part of this, where they're both trying to push each other with the Force, and they both fly backwards with an equal force. So that's action-reaction Jedi style. But if you were to look at it in this case, you have the equation FA equals minus FR. Remember, the minus just indicates direction. So it's just saying, hey, if I push you with 10 to the left, 10 to the right, you're going to push me back with 10 to the left. Okay, so you have the action force and the reaction force. So an example of this says a rocket is launched upward with a force of 100 newtons. What is the force exerted on the gas escaping the rocket? So you have the rocket is pushed upward with a force of 100 newtons. So the air escaping the rocket must be pushed downward with the same force of 100 newtons. Now, one of the hallmarks of this Newton's third law is that the forces have to act on different objects. The force upward is on the rocket. The force downward is on the air coming out of the rocket. It says a skydiver jumps out of a plane, is pulled down to the earth by a force. What is the opposing force? Now, this is a tricky one. People have a hard time with this one. So here is the earth, and there is a gravitational force that is pulling this person towards the earth. So the question is what is the equal and opposite force? And people tend to go to air resistance because they're like, oh, it's what pushes up against it. But remember, the equal and opposite reaction force has to act on another object, so it's not acting on a person. In this particular case, it is the force that is pulling the earth up towards the person. Now, you'll clearly see that the earth does not appear to move towards the person. And the reason why is if you were to look at the equation F equals ma, if there's a 100 Newton force acting on a person, that person will move or accelerate fairly highly. But if you have this same 100 Newton force acting on the earth, which is something like this, and I got tired of writing zeros, but there's 24 of them, you end up getting an extremely small number to the point where the Earth ends up accelerating like 1/1000th the distance of a hydrogen atom or something like that. So it's negligible. But there is a force that this person exerts on the Earth, pulling the Earth towards them. Next, it says a 25 kilogram boy pushes his 100 kilogram dad with a force of 20 newtons on a frozen pond below. What is the acceleration of each? Now, if you were to look at this, you have the boy who's pushing the dad with a force of 20 newtons. Okay, so what I know there is I know that the applied force is 20, and I know the reaction force is minus 20. I know that the boy, when he pushes his dad, he's doing the applied force. So I'd say the mass of the dad is 100 kilograms. The mass of the boy is 20 kilograms. In each case, you can solve for the acceleration. When you do this, you would use the equation F equals ma and F equals ma. In the boy's case, he's 25 kilograms. You would take a 20 Newton force. It's minus, indicating that he's going to go backwards, equals 25a. You would divide both sides by 25, and that would simplify to about 4/5 or negative 0.8 meters per second squared. So the boy would accelerate, but he would accelerate backwards at negative 0.8 meters per second squared. When you look at the dad, he would be a force of 20 newtons, but he has a mass of 100a. So when you divide both sides by 20, he has an acceleration of a positive 0.2 meters per second squared. So the boy has a much greater acceleration than the dad due to their mass.